finally ready to jump back into our differential forms series. And my two main goals of this series were to, well, first, give a version of Maxwell's equations involving differential forms. And that's what we did in the previous videos, which occurred a couple months ago or something. And then my next goal was to provide a proof and a bunch of examples of the generalized Stokes theorem. And that's our goal now. And we're gonna pick up by defining a couple more objects that we'll need towards that goal. So in this video, we wanna look at the notion of an M cell and an M chain, and then an integral over an M chain. So an M cell, which we can denote by sigma, is the image of a differentiable map. And that differentiable map we will denote by phi. And that goes from the interval 0, 1 to the M power. So that's like M copies of 0, 1 Cartesian producted together to Rn. So this is going to be an M-dimensional substructure inside of Rn. And it has some sort of specified orientation. So we'll talk about orientation a little bit more later, but there is some notion of orientation. And here's a really important thing, and that is that essentially the unit interval 0, 1 is the same as any interval a to b, where a and b are real numbers if both of them are closed like this. And that actually allows us to define these M cells. Instead of coming from a bunch of copies of the unit interval, we can use more convenient intervals as needed. Then an M chain is a formal linear combination of M cells. So for example, let's say you've got an M cell sigma 1 and another M cell sigma 2, then 4 sigma 1 plus 2 sigma 2, that would be an example of a formal linear combination of those two M cells. So I've written it like this, which is a bit confusing, but I think it's the most standard notation to write an M cell with this uppercase sigma. It's just unfortunate that the sum kind of uses the same thing. So I've put these hatch marks here to say that that's a letter, not summation notation. So we've got this capital sigma is a sum over some indexing set I, ni times sigma I. So those ni's are real numbers and these sigma i's are M cells. Okay, great. So now we want to look at some examples. So we'll look at the notion of a zero cell. So notice that this needs to be a map from 0, 1 to the 0. So that's 0 copies of 0, 1 into Rn. But how does that work? Well, that actually just produces a single point inside of Rn, because we want to think about this 0, 1 to the 0 power as being like some sort of universal initial point. So we can think about this, like I said, as a point. So geometrically, what's happening is a zero cell inside of Rn is just a point inside of Rn. So we could give some examples of zero cells. So like the point 1, 2 inside of R2. So that's a zero cell inside of R2. Or maybe the point 1, 0, pi, -3 inside of R4. So that's going to be a zero cell inside of R4. Okay, great. So now we want a one cell. So a one cell is just going to be some sort of curve. So maybe I'll just write this as a curve and we'll provide an example. Maybe our curve could be in R2 and it would look something like this. So, or maybe in R3 and it's got this nice looping structure like this. And let's maybe orient this so that it's going in this direction. So you might say, well, what's the orientation of a point? Well, you just give it a positive orientation, which is just a plus sign, like a formal plus sign, or a formal minus sign. So there's an example of a curve. We could maybe look at an example specifically. Let's say we're in R2 like this, and we want to look at perhaps the top half of the unit circle. So that's, let's say that's from 1 to -1. So that has a standard parameterization like this. We can take phi from 0 pi into R2, and we can define it like phi of, we could use maybe t for our variable, and this is going to be cos t comma sine t. So that's a standard parameterization of a curve, well, of the unit circle. Okay, good. Now let's look at the notion of a two-cell. So this is going to be like some sort of two-dimensional object in a higher dimensional space. So we could do something like this, maybe the cap of a sphere inside of R3. So let's say those are our three coordinate axes inside of R3. And then we've got something like the top part of a sphere. So let's say it's a sphere of radius 1. So let's say it's like that. So half of sphere with a radius of 1. So you might wonder how we can parameterize that, but we can parameterize that by being inspired by spherical coordinates. So it would look something like this. So we'd have phi would go from 0 to 2 pi cross 0 to pi over 2 into R3. And then we could define it in the following way. So we've got phi of, let's maybe use u comma v, cos u sine v, and then sine u sine v, and then finally cos v. So that gives us a parameterization. So the u angle is like our polar angle, which goes around like this. That's why we need 2 pi radians of that. And then our v angle, that's like our, well, I forgot the name of it, but that's the angle that measures from the positive z-axis. So we've got something like that. So let's look at an example of a 3-cell. And I want to look at a 3-cell in R4. So let's say we define it by the following equation. So maybe x1 squared plus x2 squared is less than or equal to 1. x3 goes between 0 and 1. And then maybe x4 is equal to 2. So it's hard to visualize this because we're in 4 dimensions, but this is essentially giving us some sort of solid cylinder. So it's solid. Our first 2 coordinates form like a disk of radius 1. Our third coordinate takes that disk from the 0 spot to the first spot, and then we're fixing it in our fourth coordinate at 2. So again, this is some sort of 3-dimensional solid cylinder inside of R4. So we could parameterize that like the following setup. So we have phi going from, so let's see, we could do 0, 1 cross 0, 2 pi cross 0, 1 up to R4 like this. And then we could maybe say phi of r theta x3 x4 is equal to the following vector equation. So r and theta, those are like giving us this bit right here, which is like our disk. So here we'll have r cos theta, r sine theta, and then x3, that needs to go from 0 to 1, so we'll just say that's equal to x3, and then x4 is fixed at 2, so we'll say that this is equal to 2. So that gives us a 3-cell inside of R4. Okay, let's clean this up and we'll talk about integrating M chains and do some examples. Now that we've got the notion of an M cell and an M chain, let's look at an integral of a differential M form over an M chain. So we denote it like this. So if our M chain is capital sigma and our differential M form is omega, then the integral of omega over sigma, that's just going to be the sum weighted by these ni's of the integral of omega over those M cells, which we've done in previous videos, and we're going to recall in this video as well. So let's do some examples. So let's say we've got a 0 form. So a 0 form is just a function. And so let's say it's f of xy, which is 3x plus xy squared. So this is a 0 form on R2. And then we've got 2 0 cells. So those need to be points inside of R2. So we've got 0, 3 and 5, 2. And then our 0 chain will be the following linear combination of 0 cells. So here we've got 2p minus q. So like I said, that's our formal linear combination of these two zero cells. And we're integrating over this function. Well, so this is an integral of a zero form, but an integral of a zero form is really just an evaluation of a function. So let's break it up via that equation first. So that gives us 2, the integral over the zero cell p of f minus the integral over the zero cell q of f, like that. But that just gives us 2f evaluated at p, which is 0, 3, minus f evaluated at q, which is 5, 2, like that. Now it's just a matter of arithmetic. So notice this is going to give us 2, and then we evaluate f at 0, 3. We'll get 0 for this term and 0 for this term, so this is 0. And then next we have minus f evaluated at 5, 2. So that's going to be 3 times 5, so that's 15. And then plus 5 times 2 squared, so that's going to be 20. So we've got 20. So in the end, we get minus 35 for this integral of this zero form over this zero chain. Okay, let's get rid of this and we'll do an example of a one form and a one chain. For our next example, we've got a differential one form. So this is a differential one form on R2, and it is given by omega, which we'll say is xy dx plus x squared plus y dy. And then we've got two one cells. So we've got this first one, which we'll call sigma 1. And this is the top half of a circle starting at -1 and ending at 1. And then sigma 2, so this is going to be a line segment from the point 0, 1. So this is going to be a line segment from the point 1, 0 to the point 2, 1. And then we've got our one chain defined by capital sigma is the linear combination 2 sigma 1 minus 3 sigma 2. Okay, now we're ready to probably parameterize both of these curves. I think that would probably be the best thing to do first. So let's see this sigma 1, how it can be parameterized. So maybe I'll say sigma 1 of t. Well, it's a bit tricky because we want to start at -1, 0 and end at 1, 0. So let's see how we can do that. We can use our standard parameterization of a circle. Maybe this is just cosine t, sine t, but then we'll let t reverse the interval from pi to 0. So we could do a change of variables to make that go slightly differently, but I think that's fine. Now we have this line segment. Well, that's not too hard to see that that's going to be a line of slope 1, and it's got a y-intercept of -1. So we can easily just think about this as phi 2t, which will go t and then t minus 1. So notice the x-coordinate is t and the y-coordinate is going to be t minus 1 because that's the line y equals x minus 1. And next, we can notice that in this case, t must go between 1 and 2, like that. Okay, so now we're good to go. We can form this one chain out of the formal linear combination of those two one cells and then take the necessary integral. So we want to take the integral over this one chain of omega. So that's going to break up into 2, and then the integral over sigma 1 of xy dx plus x squared plus y dy. Great, so that's our first bit, and then it'll be -3, the integral over this other one cell, sigma 2, of the same thing. So xy dx plus x squared plus y dy, like that. Next, we can use our parameterizations, keeping in mind what dx and dy do on these curves. So this dx we can think of as dx, dt, dt. And this dy is like dy, dt, dt, where this is our x coordinate of our parameterization and this is our y coordinate of our parameterization. And similarly for the other part as well. So let's see, that's going to give us twice, and then the integral from pi to 0, because we've reversed that interval in order to have it oriented the right way. Now we have x times y, so that's going to be cosine times sine times the derivative of cosine, which is minus sine. So that's going to give us minus sine squared t times cosine of t. So that's what we get for all of this. And then plus x squared plus y, so that's going to be plus cos squared t plus sine t. And then dy is going to give us another cosine of t. So we've got cosine of t, and then all of this is integrated dt. Okay, so that's what we have for that first one. And then the second one, which I'll fit in down here, that's going to be minus 3. Then we have the integral from 1 to 2 of x times y. That's going to give us t squared minus t, because that's our x component, that's our y component. Notice dx and dy in this case are just dt. And then we'll have plus x squared, so that's going to be t squared, and then plus t minus 1 because that's y. And again, all of this is within a dt. So we've taken this integral of a 1 form over a 1 chain and written it as like a calculus 1 type integral. So we'll just leave it like that. Okay, I'll clean this up and we'll look at a 2 form and a 2 chain. We'll finish off the example by just doing an integral of a 2 form over a 2 cell, because it's pretty easy to extend this to an integral over a 2 chain just by taking linear combinations of the integrals over the 2 cells. So let's say our 2 form, which we'll call omega again, is xz dx wedge dy plus dy wedge dz. So this is a 2 form, or a differential 2 form in R3. And let's say our 2 cell is given like this. So I've drawn 2 pictures of it. So what it really is the top half of this disk of radius 1 in the xy plane, but then it's lifted up to the z equal 2 plane. So that's what we've got going on right here. So here's like a picture of it if you were to take the slice, but here's a picture of it in 3 space. So notice we've got this half of the disk that's been lifted up to z equals 2. Okay, so we need to parameterize that. And we can parameterize that by taking inspiration from polar coordinates. So we can take phi from 0, 1 cross 0 pi to R3. So notice that is really just kind of diffeomorphic to 0, 1 squared, which would be in line with this definition over here. And we can define it like this. So we've got phi of R theta is equal to R cos theta, R sine theta, and then 2. So the R cosine theta and the R sine theta, that gives us our disk. The varying of the radius like fills it into a 2-dimensional space, and then the varying of the angle sweeps it like that. Great. And then the third coordinate being 2 lifts it up to the z equals 2 plane. Okay, nice. So now we want to take the integral of omega, where that's our differential 2 form, over this 2 cell, which is really itself a 2 chain if we just think about maybe the simplest linear combination of a single 2 cell with itself. So let's see how we can do this. So this is going to turn into a double integral. So it'll be the integral from 0 to 1 and then the integral from 0 to 2 pi. And then let's see, we need x times z. So that's going to be 2r cosine theta. And then we need to recall what dx wedge dy does. So that takes the x coordinate and the y coordinate of our parameterization, forms a 2 by 2 matrix where we've partial differentiated with respect to the 2 parameters and then taken the determinant. So we'll have the determinant, and then it'll be partial x, partial r, partial x, partial theta, and then partial y, partial r, partial y, partial theta, like that. So that's the action of dx wedge dy on our parameterization. Now we need to do the action of dy wedge dz on our parameterization as well, and that's going to be similar. So we'll have plus, and then we have the determinant dy dr, partial y, partial theta. That'll be our first column in this case. And then we'll have partial z, partial r, partial z, partial theta, like that. And then all of this is within our d theta dr double integral. Okay, nice. Now we can start calculating this. And when we do that, we'll see that this is going to be the integral from 0 to 1, the integral from 0 to 2 pi of, so we've got 2r cos theta. And then we can take these partial derivatives, and that's not too tricky. So we've got, this is cosine theta, this is going to be sine theta, this is going to be minus r sine theta, and this is going to be r cosine theta. And then for this next bit, we have, this will be sine theta, r cosine theta, and then 0, 0, because the z component is always a constant. So that's actually pretty nice. It's simple. And then we have d theta dr like this. Oh, and I just realized I should be integrating from 0 to pi and not 0 to 2 pi because we're only doing half of the disk. So this determinant will be 0 because we've got a column of all zeros. And then this determinant will give us r cosine squared plus r sine squared. So that determinant is just r, because cosine squared plus sine squared is just 1. Okay, so let's lift that result up and we'll finish it off. On the last board, we worked our integral of our differential 2 form over our 2 cell down to the following fairly simple double integral. So now we'll just go ahead and evaluate this. So notice we've got a product of a function of r and a function of theta, and then our bounds of integration are just numbers. So we can turn this into a product of 2 integrals. So we've got the integral from 0 to 1 of 2r squared dr, and then the integral from 0 to pi of cos theta d theta, like that. Good. And then this is not too hard to see. That's going to be 2/3 r cubed. Evaluate that 1 and 0. That's going to give us 2/3. And then this thing is going to give you minus sine theta. We need to evaluate that at pi and 0, but notice both of those give you 0, so this just gives us times 0, which is equal to 0, which is maybe not super satisfying, but you know, it's a reasonable thing to happen. That's a good place to stop.